Okay, this is what I meant. Yeah. Okay. If we would like to maintain, the TMP, yeah, flux. Let's recap what is flux. Yeah. Flux is the volume of the water produced, yeah, volume of the treated water produced per unit area of membrane per unit of time. That is flux. Yeah. So in order to maintain the flux, the product water production per unit of volume, per unit of area, per unit of time, we have to increase the transmembrane pressure. Why we have to increase the transmembrane pressure? Because transmembrane pressure is the pressure which force, yeah, the water to pass through the membrane, since the pores is extremely small. Yeah? That's why to compensate, yeah, after certain period, to compensate with the fouling development, we have to increase the transmembrane pressure, which is the TMP. Okay, so but if we keep constant, if we would like to maintain the transmembrane pressure, for example, we would like to maintain the energy efficiency, then we are going to uh, monitor, yeah, the reduction in terms of flux, the reduction in terms of water, treated water produced. Yeah, so this is how do we find the correlation, yeah, between the flux as well as the transmembrane pressure. Okay. All right. Before, okay, this is the fouling. Uh, to this. Okay, before I continue my lecture on fouling, these are the example that we have discussed last week. Yeah, the example. This is the only example that we have discussed last week. Okay, this note, yeah, is a handwritten note. Yeah, but please no worries if you found this is very difficult to understand. I have also included the scanned version, yeah, or from the books, yeah, but this one is the summary, yeah, summary from the book. So let's say if you would like to see a clear version of the formula, then you can always refer to the notes where I have scanned and paste into the slide. Yeah. One more thing, yeah. See, we have go through this example, yeah, on determination of membrane area required, yeah, for the desalination, and you were asked to determine the rejection rate as well as concentration of the concentrate. Yeah. So the rejection rate, everything was fine until the rejection rate. However, I would like to emphasize again, yeah, the estimation of the concentrate. Yeah. So last week, yeah, we can derive, yeah, a formula from CF. Yeah. This formula are derived from CF QF. Yeah. What is CFQF? The concentration of the feed water, the flow rate of the feed water equal to the concentration of the permit, the flow rate of the permit, yeah, plus the concentration of the concentrate times the flow rate of the concentrate. Yeah. Now the unknown is the CC. So you rearrange this equation. Yeah, so these equations are derived from the parent equation, the mass balance equation, which is this one. Yeah, so that QF is given. Yeah, I put as G here, which is given. CF is also given. Yeah, QP, yeah, I put one star over there. Yeah, QP, yeah, here is QP. So how do we get QP? QP is equal to RQF. Yeah, is given. The formula is given. So QP is equal to RQF. So R is equal to 90%, yeah, which is given here. Um, yeah, the recovery rate, yeah, small r, times 0.01, which is the QF, yeah, this is which is given, yeah, so that this is also given, and 0.044 is the CP. Yeah, where do I get CP? CP is from here. we have calculated earlier, divided by QC. Okay, where do I get the QC? Yeah, I put the 2 star over there. So QC is equal to QF equal to QP plus QC. So QC is the unknown. Yeah? So you rearrange the equation that is equal to QF minus QP. Yeah. So QF is given as 0.01. So QP is 0.9 times 0.01 because QP is equal to RQF. Yeah? So that you will get QC as 0.001. Okay. So this is how we comes to the value of QC. Yeah, you solve where do I get the value of QC 0.001. Yeah, so that's all. I have actually nothing wrong with last week lecture, but I have rearranged the equation, yeah, so that I can clarify where do I get the value of QC, where do we get the value of QP and CP. Yeah, so that I hope this will clarify how do we reach to the final answer of 39.6 kg per meter cube. Okay, all right. Okay, next, yeah, let's go back to our slide, yeah, which is on the fouling. Yeah, fouling can be defined. Okay, fouling can be defined, yeah, as a gradual decrease. Yeah, the development of the fouling can cause a gradual decrease in terms of the permit flux and the product water. Yeah, the product water which is the treated water. Yeah, so membrane foulings can be divided into 4 types. There are 4 types of membrane fouling. The first is known as adsorption, yeah, which is defined as a specific interaction between the membrane and it usually occurs on the surface or pores of the membrane. Yeah, these are the first type. The second type is pore blocking. Yeah, pore blocking. So pore blocking is the second types of membrane fouling. Yeah, and this type of fouling occurs when a solid blocks and clogs the pores of the membrane. So if adsorption, yeah, let's imagine this is a flat sheet membrane, yeah, so that the fouling is only developed on the surface of the membrane. Yeah, let me. Okay. Okay, if these are the membrane and these are the pores, yeah. So the adsorption, the membrane only occurs on the surface of the membrane, yeah. But if you are talking about pores blocking, so that indicates that the blockage is actually occurs when the fouling is actually occurs within the pores of the membrane. Okay, so the severity of this fouling depends on the size of the fold particles. And so normally the one that stick within within the pores of the membrane depends on the size of the particles. Yeah. So the third one is the cake layer formation. Yeah. So these types of membrane, this is the process of particles deposition, yeah, on the membrane surface that grows layer by layer. Yeah, so it will develop layer by layer. Yeah, so meant to say that, yeah, this formation, cake layer formation, it will take longer as compared to the adsorption. Yeah, because it's a multi layer occurrence, yeah, in multi layer clogging. Yeah, but still occurs on the surface of the membrane. The final types is the formation of gel layer. It is known as polarization of the concentration resulting formation of gel layer near the membrane surface. Yeah, I think I do have the photo, but let me find whether I hope that I still have the photos. Okay, so these are the appendix. Yeah, figure 11.41. Yeah, so these are the pores narrowing. Yeah, you can see that uh, the pores openings are narrowing due to membrane. Yeah, so second types is the blockage just now, within the pores, and this can be the absorption. Yeah, this can be the absorption, or it can be the cake layer formation. Yeah, cake layer formation, because it's a multi layer. Yeah, it can be absorption, or it can be the cake layer formation. Yeah. So the second, the figure B, figure B is actually the pause blocking. The pause blocking. This one is the pause blocking, and A is actually the gel. The what do we call as formation of the gel layer. Next week, I think I won't allow anyone to join the lecture. Yeah, if you join after 2:30, this is an online lecture. Okay, so I don't know if, even though you are not ready, yeah, you can just join the lecture so that you can reduce the interruption, and you really interfere the lectures, yeah, because it's now we are already in week 11. Yeah, you are supposed to get ready on the track for the lecture. Okay, the lecture is an online lecture. You should get ready at least 10 minutes when I have shared the link. Okay, now you keep requesting to join the lecture since 30 minutes, yeah, past the session, yeah, which is really interfere the lecture. So next week, yeah, next 2 weeks, if you cannot join before 2:30, you don't have to request anymore. Okay, fouling result in the formation of high solid concentration, yeah, on the membrane surface. Yeah, and the main issue is it can reduce the flux, yeah, where it will reduce the permit, yeah, it will reduce the permit as well as the product water. Yeah, so this has been always the issue, because whenever we design for a membrane, we are looking for the highest production of the flux, which is the treated water. Uh, in addition, yeah, whenever we would like to maintain the flux level, definitely TMP, yeah, has to be increased, so that it will force the untreated water to pass through the membrane. Okay. All right. Next is on the fouling and cleaning. Yeah. So this again exactly the same figures. This is gel. Yeah. This is a pore. This is pore blocking, and this is can be whether adsorption, yeah, or the cake, yeah, cake layer formation. If it's multi-layer, then it's known as cake layer formation. If only one layer on the surface, then absorption. So how to decide? Yeah, referring to the video that we watched just now. Yeah, so what is the parameters, that what is the factor that determine the fouling? Yeah, depend on the ingredient of water or wastewater to be treated. Yeah, so that's why normally it is better to introduce the pre-treatment, yeah, before we can start with the pre-treatment, before we can allow water to pass through the membrane. Yes, because the issue is the fouling. Yeah, because we have to reduce the effect of the fouling so that it can save in terms of cost. Yeah. Right. So next is, why do we need to do membrane cleaning? Okay, when fouling has developed, yeah, on the surface of the membrane, before we go cleaning section, let's explore this one. Yeah? Okay, uh, constitute in a wastewater, yeah, that can affect the performance of the membranes through the mechanism of foulings. Yeah? First types of the membrane fouling, fouling cake formation, sometimes identified as biofilm. So the responsible constituent, you can see the responsible constituent. That's why in the video just now, she did mention that we have to characterize properly the sample that we are going, the sample of water or wastewater to be treated, so that we can tackle the problem. We can put some remedy action, yes, to rectify or to reduce the impact, of for the fouling development. For example, for cake layer formation, metal oxide, these are the constituent which is responsible, for the fouling cake layer formation. Organic and inorganic colloids, bacteria, microbes, and concentration polarization. So the remarks damage to membrane can be limited, by controlling these substances. For example, we can employ the pre-treatment using microfiltration. Okay, next one is the scaling or precipitation. So scaling and precipitation. Scaling is not fouling. They are as in few notes. In some other note, scaling is referred to others formation on the surface of the membrane, but not exactly fouling. Okay, but in this note, they are classified as one types of the membrane fouling. So, for example, scaling, which is due to precipitation. We know that, when we mention about precipitation, definitely the fouling, so definitely the scaling are caused, by the constituent that develop the hardness, which is magnesium, calcium, so they are classified within the same group. So in this case, if the wastewater or water used contain high calcium sulfate, calcium carbonate, calcium fluoride, so definitely it can cause scaling or precipitation. So what is the issue with the scaling? Can be reduced, by limited salt content, or by adding acid to limit the formation, of calcium carbonate, or by chemical treatment. So this is exactly the same treatment how we reduce the hardness in water. Okay. Number three is damage to membrane. Sometimes if the pH, of the treated, of the water or wastewater to be treated is extremely low, so definitely it can cause damage to membrane. Damage to membrane can be limited, by controlling the substance. For example, we use a natural pH sample, but very difficult because sometimes wastewater is contain is they are at they when wastewater being produced, the pH are at 7. However, after a certain period, due to reaction, the pH might change, to 5. So this can potentially cause a problem to the membrane. Okay. All right. Next, this 11, 11 for one already explained. Now we are going to see what is fouling index and how to determine the fouling index. So approximate value for the fouling index. So to determine the fouling index, normally we have to calculate the silt density index, which is SDI. Okay, so membrane process, for nanofiltration, the allowable SDI is between 0 to 2, reverse osmosis hollow fiber 0 to 2. If you use RO for spiral wound, the allowable limit is between 0 to, this is not allowable limit. This is the limit where we have to monitor so that we can suggest for the pre-treatment. Okay, let's see the example. Okay, silt density index for a reverse osmosis system. Determine the silt density index, for a proposed feed water from the following test data. If a spiral wound, RO membrane is to be used, will pre-treatment be required? So test runtime is 30 minutes. Initial, this is the volume of the initial water. So okay, this is before we go further, I would like to explain that this is a standard test. If you would like to determine the silt density index for a reverse osmosis system, then you are going to use this volume amount, this volume of water, yeah, meaning to say that you have to use 500 ml, yeah, then you will monitor the time. Okay, that's how we monitor the performance of the membrane. So so test runtime in for this sample is 30 minutes. Initial 500 ml is 2 minutes, and final 500 ml is 10 minutes. Yeah? So calculate the SDI. So SDI, these are the formula for the SDI. So 101 minus TI, which is the T initial, minus over TF divided by T. Yeah, so in this case 100. So 1 T initial is 2 minutes. T final is equal to 10 minutes divided by total operational time is 30 minutes. So you solve for this equation, you will get 2.67. Yeah. Then you are going to compare the result that you got from this test with the result in this table. Okay. So let's see what is the conclusion. Yeah? Calculated SDI value of 2.67 is less than 3. First, yeah, in this test, they have been using the spiral wound RO. Yeah? So for a spiral wound RO, we have to refer to this row, yeah, which is the allowable, the recommended value is between 0 to 3. So in this case, yeah, the answer is 2.67. It is less than 3. Therefore, no further pre-treatment would be needed normally. So the range, the recommended range in this table actually tells us whether pre-treatment is required. Let's say if we are to apply nanofiltration or RO or RO hollow fiber or RO spiral wound, you might be thinking, yeah, why we don't have any SDI value for the ultrafiltration and microfiltration. Yeah, so SDI value is only available for the nanofiltration size and RO size, because their pores are extremely small. Yeah, so that's why I said that normally UF and MF can be used as a pre-treatment for the RO. Yeah, because before and nanofiltration we have microfiltration and also ultrafiltration. Yeah, so therefore no further pre-treatment normally needed. Nevertheless, as a practical matter, because the SDI value that we got is 2.67, very close to 3. Yeah, so it may be prudent to consider some pre-treatment to prolong the filtration cycle, because we have to always preserve the membrane material to avoid frequent cleaning, to avoid the fouling issue, so that if the SDI, since the SDI value for these types of membrane is almost to 3, very close to the value of 3, so we can consider for the pre-treatment. Okay, I have extra note regarding on SDI. It's a static measurement of resistance that is determined by sample taken at the beginning and end of the test. So that's why I said, this 500 is actually a fixed value. It's just like when we conduct our lab. We put 2.5 mils of our sample whenever we would like to measure for the COD. So regardless, your sample is rainwater, your sample is a diluted wastewater, your sample is a diluted oil, still you have to put 2.5 mil. So this 500 mil is a fixed value. Okay, so fouling index are determined from a simple membrane test. The sample must pass through a 0.5 micrometer millipore filter. So this one is the standard filter paper that we use, that normally we use to measure for the total dissolved solid, and also total suspended solid, with 47 mm internal diameter at this standard pressure. Okay, so whatever the value I put here is a standard value that have to be followed if we would like to measure for the SDI. Okay, so what is going to be the monitoring data? The monitoring data I put in red. You are going to monitor the test run time. You are going to monitor the initial time as well as the final time. So the rest, This is a fixed, this is fixed, this is fixed, and this is a fixed value. Okay, the equation in example 11.6 is defined as follows. Yeah? So T1 is time to collect the initial sample. Okay, TF is time to collect the final sample. So T1 is time to collect initial sample with feed water to pass through. TF is time to collect the final sample, the permit, and T is the total time for running test. Okay, meaning to say that once feed water pass through the membrane, then we have to monitor the period taken to produce permit or product water. Yeah, overall TF will make the significant difference. Yeah, will make significant difference if the fouling is increased. Let's say in example, the same example, the TF increased to 25 minutes. Yes, if we have the same uh, initial is before the fouling is developed. Yeah, so after certain period, we take the sample of the membrane, yeah, and we monitor how long it takes to produce the permit. So let's say this one, yeah, TF is now changed to 25 minutes, yeah, instead of 10 minutes, yeah. So change to 25 minutes so that this SDI will increase to 3.067. Okay, so this is just to compare what happened. Let's say if your TF is increased to 25 minutes instead of 10 minutes in this example. Okay, this is a very short formula, but lots of things to understand, yeah, on how we can monitor the seed density index, what is the significance of seed density index, how we can interpret the data that we got, and to relate with the fouling index, what is the recommendation for the pre-treatment required based on the value of the seed density index. And the final one is for you to know that there are a fixed the standard test, yeah, for you to, in order for us to monitor or to calculate the SDI, yeah, where we have to use the fixed volume of water to get the TI, fixed volume of water to get the TF, a fixed pressure value, as well as a fixed size of the membrane ports, which is the 0.45 millipore filter with 47 internal diameter. For information, the one that we use in our lab, the total suspended solid, that is a membrane, yeah, the filter paper, yeah, that we use to measure total suspended solid as well as total dissolved solid. Okay, so in conclusion, yeah, whenever we increase, whenever uh, the final TF increase, yeah, for example, in this case, increase to 25 minutes, yeah, so that the total SDI, yeah, will increase from 2.67 to 3.06067. Yeah, so these are the significance to show that let's say if maybe you will get TF 10 minutes after 1 week of operation. Yeah, so after 3 weeks of operation, you will be monitoring the TF equal to 25 minutes. So that's why we monitor the same volume of water to pass through. Yeah? The permit that we can collect of 500 mil, how long it will take. That is how can we define a distance. Yeah? For example, you pass through 500 mil of water through the membrane. Yeah, so that you have to monitor the time taken. Yeah, before we can collect the 500 mil of the permit. If after 7 days of operation, maybe it will only take 10 minutes. However, after 3 weeks of operation, it can take up to 25 minutes to collect the 500 mil of permit or the product water. Okay. Do you have any question regarding on this example? Okay, no question, yeah. Okay. All right, then if no question, I think we can go for the cleaning, yeah, the section for the why to clean the membrane, yeah. Membrane is subject to fouling. That is the issue. That's why we have to conduct the cleaning, yeah. So that the foreign material that can cause fouling can be metal oxide, it can be precipitation process, just now organic and biological methods, yeah. So this overall will cause the decline in terms of the permeate flow or the flux value, and of course it will increase the transmembrane pressure. Yeah, if not clean, yeah, can result in irreversible fouling, yeah, and scaling, yeah, of the membrane, and it will permanently attach to the membrane. That's why we have to always conduct the cleaning, yeah, because yeah, from the video just now, yeah, there are two types, yeah. um, Maybe we can, no, why the picture cannot be displayed. No, let me complete this one first. Okay, so one foul lens or scale have deposited, yeah, onto the membrane module, then it will lead to a more rapid decline in terms of performance, definitely. And membrane with a good pre-treatment can expect to clean about 4 to 5 times per year, yeah. If we introduce a pre-treatment, then we can only predict, yeah, we can only project for the 4 to 5 times per year, so that we can reduce, the total the operational cost. Yeah. Okay, how to do chemical cleaning? Yeah, there are few methods that can be used. There are different types of chemical treatment, including oxidation, yeah, addition, substitution, and hydrolysis. Yeah, so oxidation treatment generally involve dry or wet oxidation. Okay, so oxygen, ozone, and carbon dioxide are generally used in dry oxidative treatment, and wet chemical oxidation involve the use of nitric or sulfuric acid or phosphorus acid. Yeah, but if they use oxygen, ozone, or carbon dioxide, yeah, they are classified as the dry oxidative. And so these are the agents that used to clean the membrane. But if they prefer to use a wet chemical oxidation, then nitric acid, sulfuric acid, and phosphorus acid can be used. But these depends. This can only be determined based on the types of the fouling. If we are focusing more on the reduction on the effect of the acid, then we have to control the pH. If we are to reduce the effect of the scaling just now, then we have to introduce chemical treatment, yeah, anti-scaling, for example. And yeah, and it depends, yeah, on what types of the fouling which has been developed. Yeah, so but the rules, yeah, whenever we conduct a chemical cleaning, it's better to be conducted at higher temperature and high pH, yeah, because the cleaning process will go very well, yeah, for at higher temperature and at high pH. Yeah, so in organic foulers such as iron and manganese solid and colloids accumulated on the membrane surface. So if you would like to remove the iron and manganese, then we can use these types of acid. Yeah, so if for organic material, yeah, for organic material we can use sodium hydroxide, yeah, as the treatment agent, yeah, to reduce during the cleaning process. Yeah, so for biological and algae fouling, yeah, so we can use disinfectant, yeah, such as sodium hypochlorite, yeah, or parasitic acid, yeah, to remove the foulings and algae fouling. So that's why again we have to study the ingredient, the behavior of the water or wastewater to be treated. Once you know the characteristic of water or wastewater to be treated, then you will know which type of the cleaning agent to be used. Yeah, if you are focusing more on iron and manganese, then acid is the best uh, agent to be used. If you are concentrating more on the organic material, then use sodium hydroxide. If a biological or algae fouling, then we use sodium hypochlorite or parasitic acid. Okay. Um, okay, let me reopen my slides. Sadly, I lost the photos. Yeah. Oh, we keep giving the same. Okay. Okay, now the photo is appeared. Yeah, now already appeared the photo. Okay. Where were we just now? Okay, fouling. The problem here in the fouling, there are two types of fouling. The first one is known as reversible fouling. The second one is known as irreversible fouling. These are the figures membrane without any fouling. Yeah, this one. Yeah, these are the figures after certain period reversible fouling, and if the chemicals cleaning were conducted properly, then it will develop irreversible fouling. So this is actually the steps, the real step for the fouling condition, the development of the fouling. Okay, let's see the difference between these two uh, fouling, these two types of fouling, since we have reversible fouling and irreversible fouling. Okay, what happened? Whenever we conduct a the y-axis is the flux, G, the flux, which is the production with the volume of the product water. After certain period, you will see that the flux will will decrease due to the fouling development. So whenever we conduct a cleaning, it will come back to the original flux layer. So to the original flux volume, flux rate. So again, we after certain period, it will be fouling will be developed. Then after chemical cleaning, it will come back to the original performance. And this is what we call as irreversible fouling. Nevertheless, if we are talking about irreversible fouling, the flux has never reached to the original position, to the original performance of the membrane. The flux rate keep reducing even though after the dotted line, meaning to say that the period when the chemicals cleaning be conducted. So these are the disadvantages. If we allow the irreversible fouling to occur, to some extent it might cause the crack of the membrane. So I remember that there is a membrane technology that they use in Negeri Sembilan to treat groundwater from a tube well. So what happened that they keep telling me that they have been collecting kind of solid in the treated water after pass through the membranes. So there is first of all, first of all, yeah, for a normal operation of membrane, we shouldn't be collected any kind of solid, because to pass through a membrane. Even the bacteria cannot pass through the membrane. So how come you can collect the solid in your treated sample, in your permit? That is the first story. The second story is there is no way, even though the fouling has been developed on the surface of the membrane, there shouldn't be any potential for the solid to pass through. So this might be the third case. The third case where where the situation known as irreversible fouling. Because irreversible fouling means to say that the fouling has been developed on both sides, of the membrane. Then the following stage, it will cause cracking of the membrane. So that will allow the solid to pass through, to easily pass through the membrane without any proper filtration. Okay, so you can see these are the effect, when we allow irreversible fouling to occur. So that's why we have to avoid. It will not occur if the chemicals cleaning be conducted as per schedule. You can see for reversible fouling is common to occur, and whenever we conduct the chemical cleaning, the performance of the flux rate will go back to normal after the chemical cleaning. However, if you are talking about irreversible fouling, it will never come back to the baseline. It will always keep reducing the performance. So in other words, whenever you allow the irreversible fouling to occur on your membrane, uh, you are about to spend you are about to spend some more money to buy a new set of membrane. That's why this is not a good story lah. This is situation that we would like to avoid. For reversible fouling is common. We cannot avoid but we have to plan. We have to plan for the proper cleaning. Okay, factors that can contribute to foulings including the particles in the source water, inadequate process condition, and improper membrane filtration material. So this can cause severe flux decline, the production of the treated water, rising the energy cost because we have to increase the TMP, and we force water to pass through the membrane, and flow is restricted through the pores, and definitely it will affect water quality. That is a common sense. That is common sense. Okay, let's see the accumulation of the scale. This is actually the microscopic photos, accumulation scale on the membrane brine space. Okay, and these are the biofouling. This is a spiral wound. A spiral wound. A flat sheet membrane in the form of a spiral wound, and these are the in a reverse osmosis. This one is a spiral wound, also a spiral wound system. You can see on my left side is the membrane. Here's a new brand membrane. On my right side is a full a membrane after reverse osmosis. Okay, so in summary, membrane fouling is described as potential deposition and accumulation of the constituent in the feed stream on the membrane and is considered as important parameters in the design and operation of membrane, and also it can affect the pre-treatment needs. So cleaning requirement, operating cost, and overall performance. So that's why we have to first get to know the characteristic of water or wastewater to be treated, so that we can introduce the pre-treatment. This is very important steps to avoid the development of the fouling, to avoid the damage to the membrane. In other words, so that we can prolong the period before we have to conduct the chemical cleaning. But if you would like to suggest not to conduct any pre-treatment, for this reason, a planned, a frequent chemical cleaning has to be conducted. Okay. All right. So in general, this one already explained. The forms of the membrane build up of the constituent in the feed water, formation of the chemical precipitation. This one the scaling just now, and damage the membrane due to the reaction, especially if you are dealing with extremely low pH Yeah, low pH in the water or wastewater to be treated. Okay, all right. All right. Next, I think we can spend some time to watch a video. This one. This one already. I have one short video that I would like you to see. I would like you to watch this video because you will see the real formation of fouling. Yeah. Okay. There is no background voice. Yeah, you can see the process. Yeah, how the fouling occurs. Yeah. Okay. So now you see. These are, you can imagine, these are the pores of the membrane. Yeah. So the water that can, only water molecules, yeah, should be able to pass through the pores of the membrane. Yeah. The rest should remain on site, yeah, before it can pass through the membrane pores. Yeah. So you can see now there are multi-layer development, yeah, which is known as cake, yeah, cake formation, and how small the water molecules, so that it will allow to pass through the membrane pores. Okay.
Hi, this is Simon Judd. There's just one aspect of our work which is much more easily explained if you can actually see it, so I'm just going to run through it now. So here we have our membrane channel face on, so you can actually see what's happening inside. It's filled with sludge at 3 different concentrations, from 15 grams per litre on the left to 23 grams per litre on the right. I'm just going to run this video so you can see what happens to those air bubbles as they pass through that channel. So you can see that, for one thing, the bubbles at the two highest concentrations are actually larger than the ones being produced at the lowest concentration, but also the bubbles at the lowest concentration on the left hand side there are scouring more or less the whole area of the membrane, whereas if you look at the ones being generated at the two higher concentrations, they are tending to sort of veer towards the center of the membrane channel. And that means that at the end of the experiment, once you drain the sludge and have a look at those channels, you find the two highest concentrations, there is a definite pattern developed where at the sides of the membrane channels, that is where you find the clogged solids, but also a bit in the center between the two ports of the coarse bubble aerator. So really what that demonstrates is that sludge concentration has quite a significant impact on sludging. If you just look at the same membrane channel at the lowest concentration, there wouldn't be any sign of any sludging at all. And that's basically it.
If you want to go fast.
All right. So let's move to our next slide. I think I have to open the slide. Because I have lost the image. Okay, the next topics is very short. Yeah, very short. We have three slides. Yeah, first is on fouling. Second is on. Are you sure that we have finished on the something? Okay, already. Okay, second is on the osmosis. Yeah, how can what is reverse osmosis? What is the difference between osmosis and reverse osmosis? And it will be followed by the calculation. And the third one will be on designing designing of the membrane bioreactor. Okay, all right. So let's proceed with our second topics. Second subtopic is on the what is osmosis. We have watched the video last week, very short video to explain osmosis. So osmosis is a process by which water pass through a semi permeable membrane. So and it's actually move from a less concentrated solution to a more concentrated solution, in an osmosis situation. For example, for if you have water molecules one side, you have a membrane, so the water molecule will remain. However, the salt molecule will pass through, to the other side, because it can pass through the membrane. That is the osmosis situation. So in other words, the pure water pass through the filter to contaminated water in order to equalize the concentration. The Next, what is reverse osmosis? In reverse osmosis, an applied pressure is used. So the main concept is we have to apply the pressure. That is reverse osmosis. So in this case, an applied pressure has to be used to overcome the osmotic pressure. Because in osmotic pressure, is in a normal condition. Water will pass through from less concentrate, salt material will pass through from less concentrate to more concentrate. Yeah. So in reverse osmosis, since we would like to work in different way, that's why a pressure is required. That's why we have to apply pressure to push the water from high concentration of contaminants to low concentration of contaminants. Because in osmosis situation, from less concentration solution to low concentration, from less concentration solution to more concentrated solution. And in reverse osmosis is moving from the high concentration to low concentration. So in this case, they use the example of salt water. Salt water. On the other side, that we have fresh water. So that you can see whenever we apply the pressure, we apply the pressure, and only the fresh water will pass through the membrane materials. Okay, this is again the example of the reverse osmosis. In osmosis condition, whenever we have a semi-permeable membrane, this is water solvent, this is the concentrated solution. So this is the situation when the water molecules will pass through from low concentrate to high concentrate. On the other hand, for a reverse osmosis, these are the main idea. We have to apply the external pressure. Applying the external pressure will allow only the water molecules to pass through the membrane, and the remaining salt will be on the side. So the concept here is from high concentration to low concentration, because we have fresh water on this side. So for osmosis, low concentration to high concentration. Okay, right. So this is again an example of the osmotic pressure, where low concentration of water molecules to pass through into high concentration. But for in a reverse osmosis condition, we have to apply pressure, then only water molecules will pass through the membranes materials from high concentration to low concentration. Okay, so what is osmosis? What is osmotic pressure? So osmosis is the process in which a liquid pass through a membrane and permit the passage of the solvent molecule, but too small. That's why we have to apply the pressure. If without hydrostatic pressure, so this is the situation whenever the hydrostatic pressure that we apply is greater than the osmotic pressure. because the osmotic pressure, water will move, right? In the osmotic pressure, uh, it will move from low concentration to high concentration this way, right? It will move, water will move in this direction. So however, whenever we apply the hydrostatic pressure, it will overcome, yeah, the osmotic pressure. This allow water molecules to pass through the membrane. Yeah? Okay. Next is the where is reverse osmosis used? Yeah? So the most common use for RO is during desalination of water. Yeah, so this means in a reverse osmosis system, yeah, for example, like water and the is that the pressure of water going into the pressure vessel. So we have to apply about the recommended value of the pressure used is around 55 bars. Yeah. So, but if you are to treat the brackish water, since it's less concentrate as compared to seawater, so we can use up to uh, as high as 450 only. Okay. Right. So in conclusion, yeah. So in conclusion, for a membrane a process characteristic, yeah, for if we use microfiltration, water, monovalent ion, multivalent ion, and viruses can pass through. Bacteria and suspended solid cannot. So please don't tell me that we have been using a membrane technology, doctor. However, we keep collecting treated water with high concentration of total solid. That is ridiculous. Meaning to say that something wrong with the membrane system. Yeah, because so suspended solid should not pass through, even though the biggest pore, the biggest pore among the membrane is microfiltration. So in this case, yeah, you can see that suspended solid cannot pass through. So that's why I said ridiculous to have to collect a suspended solid in your treated sample or in your permit. For ultrafiltration, yeah, in this case, viruses, bacteria, and suspended solid cannot pass through. Yeah, if you use nanofiltration, suspended solid, bacteria, viruses, and multivalent ion cannot pass through. Yeah, and last one is a reverse osmosis. Yeah, so in reverse osmosis, yeah, monovalent, multivalent ion cannot pass through, including bacteria, viruses, and suspended solid. So monovalent ion, for example, like sodium. Yeah. So multivalent ion, for example, like calcium. Yeah. Okay. Because calcium is 2 plus, kan? Yeah. Okay, so concentrate. Yeah. So what happened? Yeah, whenever we have desalined the water, we use for example, a reverse osmosis system. We will be collecting the very high concentration of salt. Yeah, I mean the what happened to the retentate? What happened to the concentrate that produced from a membrane technology? So the disposal option can be ocean discharge, can be surface water discharge, but all subjected to pre-treatment. Can be land application. Land application has been used for some low concentration of brine solution. Discharge to wastewater collection system, deep well injection, evaporation ponds, and control thermal evaporation. This can also be the option, yeah, because when you apply evaporation process, yeah, what happen? It will separate the salt as well as the water. Yeah, so these are the main rules of evaporation. That's why in following 2 weeks, yeah, we are going to study on desalination technique using solar distillation. Yeah, so solar distillation, we use this concept. The major process is the evaporation because this process can separate water and salt. Okay, so these are the more common methods that can be used instead of reverse osmosis for the salt removal. Okay, let's see the example. Yeah, estimate quantity and quality of waste streams, yeah, for a reverse osmosis system. The RO system is to produce about 4,000 meter cube per day water to be used. Yeah, so this one is the flux rate. Yeah, this one is the flow rate. Yeah, so assume that both of the recovery and rejection rate equal to 90%, and the concentration of feed water is 4,000 gram per meter cube. Yeah, so this one is Q, the concentration of the feed stream. So this is a concentration. So this one is the CF. Okay, CF, 4,000 gram per meter cube. These are the CF, which is also equal to 4,000 milligram per liter. Okay. So first, determine the flow rate of the concentrated waste stream and the total amount of water that can be used. Combining the equation, 11.41 and 11.39 result in the following expression. So QC equal to QP1 minus R over R. So determine the concentrate stream flow rate. So QP is equal to 4,000 is given in the question. 1 minus R, 1 minus R, R is the recovery rate divided by R. Divided by R, in this case, R, divided by R, again the recovery rate, which is 0.9. So determine the total amount of water that must be used to produce 4,000 meter cube per day of RO system. So in this case, determine the total amount of volume of water must be processed. So QF equal to QP plus QC. So 4,000 plus 444. So these are the total amount of water that must be processed if we are to produce about 4,000 meter cube of RO water. Okay. Okay, example number 2. Example number 2, we are to calculate the area and power requirement for an electrodialysis system. Determine the area and power requirement to demineralize about 4,000 meter cube per day of treated wastewater to be used for industrial cooling. And this has unit comprised of 2,240 cells. So number 1, you are given that the TDS is equal to 2,500. The ion and anion concentration is about 0.01 gram equivalent per liter. Okay, let's see the solution. Okay, this is the final slide. For this one, so efficiency of salt removal 50%. The current efficiency is 90%. The CD to N ratio is about 500 milliampere per centimeter squared, and the resistance is about 5 ohm. So calculate the current. First of all, you calculate the current. So I equal to FQ N mu over NE. So I will also upload this note, the handwritten note in our slide. So in this case, F is equal to 4,000. Then this is too small. Okay. N as well as the E value is also given, so that you will get the current equal to 1003.4 ampere. So determine the power required. P is equal to RI triple of 2 or 3. And P is equal to 5 ohms. P is equal to 5 ohms times 103.4 minus 53.477. Then you will get 53.5 kilowatt. Okay, determine the required surface area. Okay, CD is equal to 500 normality equal to 500 milliampere. So the CD to N ratio is about 50. CD to N ratio about CD, so that whenever you would like to calculate for the CD, then you can use this equation. So the required area, okay. Alright, so determine the required surface area. So CD 500 times 0 milli. So you get 5 milliampere, 5 milliampere per centimeter square. Yeah. Then you calculate the required area. Yeah, the required area is equivalent to 103 ampere just now that you calculated times divided by 10 to the power of 3 divided by 5 ampere. Okay, and and assuming a square configuration will be used to determine the dimension each of the membrane. Yeah? So this is a standard. Um, this is a standard. Yeah? Whenever you would like to propose, then of course you have to check. Yeah? By hoping that you always get to the higher value as compared to the calculated. Yeah. So assuming a square configuration, so this one is very clear that you have to assume a square configuration. Yeah, when you say that they have been using this, yeah, for the standard. So it means the dimension, yeah, of Aceh, of each side of the membrane. So for slight dimension, since you have got the value of 20,600 here, yes, 600, so that for the slide dimension you will get, because this is a square configuration, yeah, that's why we can use square root. Yeah, so each dimension the size is about 143, yeah, centimeter, 143 centimeter. Okay. All right, so this is the third example, because the first example of the membrane was belong to last week lecture. Then we calculate the STI, and now we calculate the power, yeah, power required. Yeah, then we shall go to final section, which is on the membrane bioreactor. Before we proceed with the membrane bioreactor, I would like to share a very short video, only 8 minutes video, about the sewage treatment plant based on MR, membrane bioreactor.
Get back in style with up to 66% last points cashback. Shop Gen Gaya sale.
Memanglah potik. Nabi kata,
Okay, so basically, membrane bioreactor is a combination of a membrane process, and like maybe normally we use ultrafiltration or microfiltration, because the pores is not too small, and also we would like to maintain the MNSS, means liquid suspended solid. Yeah, otherwise it will be clogging very fast. And that's why only UF and MF, right, are being used in a membrane bioreactor, because it's a system where they combine with the activated sludge. Yeah? So these are the units of the membrane bioreactor. Yeah. So the advantages of integration. Yeah. When you integrate of the activated sludge as well as membrane bioreactor, we can retain more MLSS. However, whenever we employ membrane bioreactor, we have to apply recirculation because too high MLSS can cause clogging of the membrane. So there are two main concept that you have to understand. Yeah, whenever we apply membrane bioreactor, three. Yeah, sorry. The first one is membrane bioreactor are normally used for the treatment of wastewater because they are integrated system. They can be an integrated system for an activated sludge. Number two, membrane has to we have to apply recirculation to avoid the clogging of the membrane because without applying the recirculation, the MLS will be too high. Okay. Third, for membrane bioreactor, normally the UF and MF will be used. Yeah, they use the bigger pores of membrane, which is ultrafiltration or microfiltration. So these are three main concepts that you have to understand whenever we apply a membrane bioreactor. In this example, they use a submerged bioreactor. Uh, but if MLSS is not the issue, yeah, we can use the membrane bioreactor as a separate unit, yeah, meaning to say that you put outside, yeah, outside the tank of the activated sludge. Okay, this is what I mean. Side stream MBR with the external pressure driven membrane filtration. So if you put membrane as a separate unit in a bioreactor instead of as in a unit, with the bioreactor, which is the activated sludge tank just now. So in this case, we have to apply external pressure driven, yeah, because it works like a normal membrane where it's become and you see here the flow is influent and bioreactor inflow into the membrane and it will produce the permit and it will recirculate as the influent again, yeah, as compared to the submerged system with internal vacuum driven membrane filtration. So it will directly produce the permit, yeah. However, recirculation still be applied, yeah, from one tank to the pre-aeration unit, yeah, pre-aeration unit. These are the example of submerged membrane bioreactor. Now you can see this is the anoxic tank for denitrification. Yeah, and permit have been collected. At the same time, when we have the aeration, this is what I mean when we apply the MBR, we have to, whenever we apply the submerged system, the aeration should be working at the same time. Yeah, the aeration should be working to avoid the clogging, and there will be recirculation of the sludge. At the same time, they will keep collecting the permit. Okay, so low one is for the aeration for BOD removal in the tank. Yeah, we run during operation at the time of the cleaning, it will be in the off mode. Yeah? So this blower is for the BOD removal. But during the time of cleaning, it will be in the off mode. Okay, so blower 2 is for back pulse, for air during physical cleaning of membrane to avoid the blockage. So this in operation of the MBR, blower 2 will be turned off mode. During the cleaning only it will be turned on. This blower 2. Okay, so there are different types of chemicals. Chemicals enhanced bed wash, one in a fortnight, for avoiding residual fouling. For chemical cleaning, for irreversible fouling is required within 6 to 12 months. Okay, what happened? Okay, just now, the one that we have seen just now is the system in the submerged system. In the submerged system, again, this is the blower 1 for the BOD removal. Blower 2 is for cleaning purposes. And the next video will be a separate unit where you can see that membrane will be located outside the bioreactor unit. Okay, this is the NOZ tank body electrification. Again, we have blower for the aeration. Okay, in this case, the treated water will pass through the membrane module and it will be perfect. Okay, again, there will be sludge recirculation. This one will cost less maintenance in terms of to clean up the membrane, because the membrane unit is outside the activated sludge system or the tank. However, we cannot retain high MLSS because a membrane will act as a filter media, like we have the for example, we use a filter media in our tank to allow culture to develop within the pores of the membrane. But for the membrane module, which is as a separate unit, as a side stream unit, so less maintenance as compared to the submerged system. So in this condition, membrane module is considered as a post treatment because the treated water from the tank will pass through the membrane module.
Discover endless possibilities with Delta, the ultimate modular sofa.
Okay. In this module, you can see that only one blower are being used because this is the blower to produce the bubbles for the odor removal. But for the membrane module, there is no second blower because they use the cleaning chemicals only. They use the chemicals as compared to the submerged system. They need two blowers because we cannot allow too much MLSS. This is the second lowest using for the cleaning. We cannot allow too much MLSS to stick the suspended solid to stick within the pores of the membrane to avoid the clogging. Okay, so I think that's all. The video on membrane bioreactor. So let's continue our lecture because we have a calculation that we have to go through. Um, that we have to go through today for the membrane bioreactor. Okay. Alright, uh, 15 slide, but I believe that we can complete this within 20 minutes. Yeah. So a membrane bioreactor. Now this is the comparison, yeah, of the conventional activated sludge and also a membrane bioreactor. Yeah, so that you can see here what is the major difference. Yeah. So in this case, there is a membrane, yeah, retained as a submerged unit of the activated sludge of the bioreactor. Yeah. So the advantages of employing this, definitely we are to produce a better quality of effluent. Yeah, but the maintenance is also fairly bad lah, yeah, because we have to conduct the frequent maintenance, especially for a submerged system, because it's require frequent maintenance. As you can see in the previous video, that we need at least two blowers. Yeah, first to supply for the BOD removal, and second blowers is to remove the suspended solid, yeah, which is can be potentially cause clogging of the membrane. Yeah. Okay, it is possible to operate the MBR process at higher MLSS concentration compared to conventional system. Yeah, so this indicates that, yeah, whenever you apply a submerged membrane bioreactor, you can treat higher concentration of organic loading rate. Yeah, especially when you are dealing with too high concentration of suspended solid. Yeah, because they can allow some suspended solid to retain, yeah, within the pores of the membrane. So this one is this one is the simple schematic describing the MBR process. Yeah, so these are the membrane. So these are the clean water. So it works like a filter lah. Yeah. So it's a primary treated water. This one is a separate unit. Yeah, whenever they use a membrane as a separate unit, yeah, as a post treatment, the top diagram, the bottom diagram is the UF or membrane as a submerged system. Yeah, as a submerged system. Okay, MS membrane has a better effluent quality. Yeah, therefore the treated water can be reused directly. Has a low rate of sludge production, so it can reduce the cost for sludge processing. So these are the advantages lah whenever you apply you apply the membrane bioreactor. Yeah, so the high quality of effluent, definitely. Less sludge produced, definitely, yeah, as compared to a conventional system. Okay, these are the figures, yeah, of the activated sludge. These are the membrane sheet, the one in gray, yeah. So that treated water at the middle part, yeah, of the within the membrane, so that to see the air covering, yeah, has to be applied, yeah, from the first blower, because, yeah, some of the suspended material might stick on the membrane sheet. Okay, this is the example of the real photo for a cross bubble aeration in membrane bioreactor with the system where these are the membrane unit lah. Aeration is crucial for both hydraulics and biological performance, yeah, because for biological it has to be used for the BOD removal. For the hydraulic purposes, they are to be used for the air covering, yeah, to avoid the particles to stick, yeah, within the pores, to avoid the particle to stick within the pores of the membrane sheet. Yeah, so that's why air is crucial, yeah, for two reasons. Yeah, so air diffusers are fixed at the bottom of the aeration tank. This is depend on the configuration. Yes, at the bottom, normally at the bottom, because it will supply the oxygen for the BOD and both for the as covering of the solid. Yeah, bubbles rapidly rise from the bottom and suspend the solid and keep them from settling. Yeah, additionally, the air bubbles supply for biomass. Yeah, and sometimes it will supply the oxygen to microorganism. Okay, what is the advantages? Yeah, whenever we apply for the moving bed bioreactor, first, I already mentioned just now, it will produce a better quality of effluent. Yeah, second, you will produce less sludge. Yeah, so that it will reduce total operational cost. Third, a small footprint. Yeah, if you are looking for a system where very good quality of effluent with a limited area, limited space, then you can go for the yeah, because no clarifiers are needed and no pre-treatment, no tertiary treatment are needed. Yeah, because you already use the MBR. So remember, why do I say no pre-treatment is required? Because for the moving, for the sorry, I keep mentioning moving back bioreactor. For a membrane bioreactor, normally we use ultrafiltration and uh, microfiltration only. Yeah, a consistent performance. Yeah, MLSS high, the organic content in the water can be retained and can be much higher than conventional activated sludge. Yeah. Okay, the disadvantages, yeah, high capitals and operational costs, yeah, operation complexity and required trained personnel. Yeah. So this has been always not only for the membrane bioreactor, it happened to all types of membrane. Yeah, it's a require high capital and operational cost, and also it has to be taken care, yeah, by someone who are well trained. Okay. All right. So our final section today will be the example. The example. Okay. Um, the example for the okay, membrane module process design calculation. A design wastewater flow about 7,500 meter cube per day is to be treated with a membrane bioreactor wastewater treatment system. The design membrane module properties are: J is given as 12 liter hour per meter squared. Module packing density is about 120 meter squared per meter cube. Specific aeration demand, which is the SAD, is 0.3 meter cube air per hour per meter square of membrane. Calculate the required membrane area, membrane module volume, and covering airflow rate. Okay. Membrane area, this one is a common unit. Yeah. Whenever we use a flux, I remember in my notes that we have J, yeah, is equal to V or over A times T. Yeah. So that in this case that they have J is equal to Q times Q times Q times A. Yeah. In this case they sorry they use Q divided by A. Yeah. In this case, we are going to calculate the area. So that you rearrange the equation. So Q over J. Okay, J. So A becomes the A becomes the unknown. Yeah. The membrane module volume is then calculated as VM AM over the module packing density, yeah, represented by sigma, and the covering airflow rate, to keep the membrane getting full is calculated using this formula. So this gives the required covering airflow in this unit. Okay, so maybe you can spend a few minutes to read the question. Yeah? Okay, okay, let's continue solving this question. Very short. I think the question is very long than the solution. Okay, required membrane area. So you are given the flow rate. Yeah, so you are given the flow rate from in meter cube per second. Then you change to meter cube per hour. Yeah, so you have the formula K8 Q over J. You are also given the flux rate, which is 12. So you substitute the value, then you get the area. Yeah. And next, membrane module volume equal to A over density. So A just calculated, density is given. So density here is referring to module packing density. You will get the volume. And lastly, to calculate the required scouring airflow, this can be calculated using a specific can be calculated from specific aeration demand times A. Yeah, so in this case, you are given the specific aeration demand is about 0.3 meter cube air per hour meter squared membrane. So in this case, these are the flow rate, of the aeration unit, so that times the area, so that you will get the required scouring airflow. So this is the scouring airflow rate needed for the membrane module, typically provided by a coarse bubbles diffuser system. Yeah, this is the scouring rate. So since there are two functions, of the oxygen, oxygen that supply the aeration. First, we have to calculate the rate of the oxygen required, to for the BOD removal. Yeah, remember that we have calculated earlier. We have calculated for the nitrification, denitrification, and we know that we can reach to the calculation where based on the BOD loading, we shall get these are the amount of oxygen required. Yeah, so that now since we have incorporated or integrated the membrane bioreactor, so we have to consider the required scouring airflow too. Yeah, so two sources. Yeah, I mean the airflow into the membrane bioreactor, which is submerged in the activated sludge system. There are two functions. First, for BOD removal, as calculated before. Second, for the required scouring airflow. This is to avoid the clogging of the pores of the membrane. Okay, all right. Lastly, I would like to share with you. This is actually from my journal published by my master student last year. We use a pilot plant, a pilot plant membrane bioreactor located in Ilan Negeri Sembilan. So this is a treatment of wastewater from a food and beverage industry integrated with the membrane bioreactor system. This is a pilot scale. Yeah, so we have published a Q1 paper so that uh, to see the performance at a pilot scale level. At pilot scale level, meaning to say that at uh, at level where the factory can use to treat the produced wastewater. And these are the schematic diagram. Charts, conventional activated sludge plus the membrane bioreactor. If you can see the flow, this is the real schematic diagram. This is also published in the journals. Even the photo here also published in the journals. And first they have equalization tank. Yeah, this is the real treatment process, in the factory, and they have chemical reaction tank. They have dissolved air flotation. You can see there are few steps before it can reach the membrane modules and feed pump. So this is the feed water comes in and it will go into the activated sludge reaction tank, and also where the membrane module is inside. So a permit will be produced. This will be the permit valve, so that they can collect the treated water. So this is where the chemicals are being supplied, for the chemical cleaning purposes. These are the uh, the flow where the chemical are being supplied for cleaning purposes. At the same time, they will also return. They will also employ some return activated sludge for recirculation. So it will return to the equalization tank. So because we have to apply recirculation. Okay, um, so and don't forget, this is the blower. Yeah, so the unit with the membrane bioreactor has to be supplied with the blower. This is the diffuse valve, for air cleaning, and this is the blower to supply the oxygen. So remember in our notes, in our video just now, whenever cleaning are being conducted, this one will be closed. So in normal operation, blower will keep working. Yeah, uh, except during cleaning. Okay, so these are the specification, of the membrane module. These are the real specification for the membrane bioreactor used in the pilot plant. So okay, so brand, uh, they use the site. They use the ultrafiltration. They use they use two types. First is hollow fiber, second is the flat sheet. For the hollow fiber, they use the size of um, MF. And they use the size of MF. For the flat sheet, they use UF. Okay, so recommended MLSS is this one. So the TMP, the flux rate produced, you can see that the flux rate produced are more or less the same. If we compare between the hollow fiber as well as the flat sheet. So these are the characteristics. These are the specification. The specification. Hollow fiber can also exist in the size of UF. Flat sheet can also exist in the size of MF. So this is how do we arrange, which one come first. So it depends on the ingredient of our sample. Okay. All right. So I think that's all for our lecture today. Before I end the session, in next week there will be no lecture because it will be visit. Visit is compulsory to everyone. It's compulsory to everyone. No excuse will be accepted except you have a medical reason. Uh, yeah. Please ensure that there is none of you have symptom, about the COVID-19. Please ensure that you are in a good, in a well, in a well condition to join the visit. So as I said just now, only the medical reason will be accepted because the visit shall be conducted during lecture time. It's not it's not outside the lecture hours. So it's compulsory to everyone. So because this is only the period where you can, this is the only moment that you will see the real water treatment plant. So please take this chance to explore more, to understand better on the real operation of water treatment plant system. Okay. All right, before you go today, I have one assignment. Remember that we have planned for 3 assignments, so that you are going to submit this assignment in 2 weeks' time, which is in week 13 before your test. This is a very simple and short assignment. Um, Very simple and short assignment. We are going to spend some time to discuss about this assignment because this is a breakout session. Okay, so these are the explanation. Assignment 3, submit this assignment in a slide form. So my assignment is always short, because I don't want you to submit in a report. yeah, as a report. So submit in a slide form in week 13 on 21st of June 2022, yeah, as a group work. You are going to submit based on the topics, because we have two topics here. First, UV disinfection, group 1 and group 2. Topic 2 is solar distillation. Both topic uh, have the same level of difficulties, and both are very interesting. Yeah, so I leave it to you to decide your group member. I think we have 24 now, 24 students, so 6 students in each group. Yeah, because group 1 and group 2 will be working on UV disinfection, while group 3 and 4 will be working on the solar distillation. Okay, so you only need to answer the question. Since I have divided to 6 questions, so each of you, let's say group 1, we have student A, B, C, D, E, F, 6. So that student A will be answering question number 1, yeah, 1 slide. Student B will be answering question number 2, so it will become slide number 2. Student C will be answering question number 3. Student D will be answering question number 4. Yeah, student E will be answering question number 5, and student F will be answering question number 6. Yeah, it's actually, you don't have to spend time to discuss with your friend, because looks like it's a group work, but you have to work individually, because you submit as a group works, but you have to write down your name, yeah, because this will be evaluated individually. In each of the slide, please write down your name. Okay, so present in week 13. So maybe each of you can spend 1 minute, yeah, to present the findings. 12 to 15 minutes per group, and minimum 7 slides, including the front page. So on the front page of the slide, only the title and the group numbers, because the name should be appear on each slide, yeah, because different names, yeah. So and maximum of 9 slides. Please do not exceed 9 slides, yeah, but it's highly recommended to have only a minimum of 7 slides lah. Okay, so same goes to topics number 2. I will leave it to you to decide the group's member and to choose, yeah, the topics. 2 group will be discussing on the, will be presenting on the UV or disinfection. Group number 3 and 4 will be working on the solar distillation. But do not discuss, group number 3 and group number 4. Let's say you have the same question. Please work individually, because this is an individual work. We are not going to present the same output for question number 2 for student A in group 3 as student A in, student B in group 3 and student B in group 4. Yeah, because that is considered as a wrongdoing. Yeah, so please work individually, because I think you will take maximum of 30 minutes. Yeah, you don't have to discuss among, even amongst the group member also, no discussion is required. One of the group member need to compile the slide which you have prepared individually. Yeah, so I repeat, yeah, student A will be answering question 1, and student F will be answering question number 6 respectively. Okay, so you decide the group members, you decide the topics that you are going to explore. Okay, all right, so I think that's all for today. Everyone, thank you very much for your attention, and please accept my apology for the interruption. And I will see you again next week before 1:45. It's good if you can get ready. If you get ready in our faculty at 1:30, yeah, that will be great. Yeah. Okay, so with that, I thank you and have a pleasant evening, everyone. Bye.